The other thing that you need to remember from your childhood is the determinant of the matrix. So now we have matrices, and we want to characterize our matrices. There are a few different fingerprints and signatures of the matrices. Determinant is one of them, and how it is computed is, so take the a 1, 2, 3, 4 four-dimensional example. You remove the first row, and then take the first component. So this will be A, and take everything. So remove these two, and then what is left is a two-dimensional matrix. Multiply A by that, and then do the same thing to the second element, and the third and the fourth. So for the second one, you eliminate the pink columns and rows here, and whatever is left in the blue, you keep it here, and you multiply by the element that is in the intersection of the row and column. And then every other one you do plus and minus. And now this becomes a determinant again, and you repeat that and until you compute it. Now, this is why this is important. This is a measure of the size of your matrix, of the norm of your matrix. If you do this and you get 0, you cannot invert your matrix. Okay, and that's very important. If you cannot invert your matrix, then a lot of things that you need to do, you have to be very careful with it. So usually when we want to invert a matrix, we should try not to invert a matrix. Just keep it in mind, don't ask why, because it's a very costly thing. It's a very costly thing. And I show you better ways to do that, where you can avoid inverting matrices. But basically, if the quick check to see if something is invertible or not is to check the determinant. And all of this that I told you, in PyTorch you can do in one line, torch.dit of the matrix, and that gives you the determinant of the matrix. We will look at examples of that when we do the hands-on session. And then there are properties of determinant where if you take the transpose, determinant doesn't change. So you see that this is the determinant of a matrix is 1 over the determinant of the inverse of the matrix. And that's where you see if this is 0, it doesn't exist. So as you see, this is a fingerprint of our matrix. How much time do we have? How much longer can I go?
A few more.
Okay. The other one, which is very useful, is the thing that I just told you not to do. The inverse of a matrix. What does it mean? If you have matrix A, the inverted matrix is the matrix that you multiply by our original matrix to get 1. And what is 1 in the matrix algebra? Is the identity matrix, right? So where it's 1, 1, 1, 1 on diagonals. And it doesn't matter which side you multiply the matrix from. The special case for matrix inversion is the easiest one. If we have a diagonal matrix where we have A1 to AN on the diagonals, when we invert it, we get 1 over A1 to 1 over AN on the diagonals. So you just invert each of these components, and that is the inverted matrix. If you want to prove it to yourself, take this, multiply it by this, and convince yourself that you get the identity matrix. All right? And you can do it in PyTorch. Actually, try that in the Colab notebook when you're doing the hands-on. Take a matrix, which is diagonal, and then invert it and multiply and see. All right. The other property of the matrix, which is this is crucial and it's very easy to calculate, and is invariant under a lot of things. That is the trace of the matrix. Remember this. We will come back to this in the future. The trace is when I take the diagonals of the matrix. It doesn't matter if it is diagonal or not, and I sum it up. Sum everything on the diagonal up. That gives me the trace of the matrix. And the properties are, the trace is given by the sum of eigenvalues. What are eigenvalues? We will get to that in right after the break. And if you transpose the matrix, the trace doesn't change. The trace is invariant under how you multiply two matrices, and the trace of the sum of two matrices is the sum of the traces, and some other nice properties. How do we do it in PyTorch? Torch.trace, and that's it.
Where do we use trace?
We will get to it very soon. Where we will use trace, and the answer is we will see it very soon. All right. So let's stop here right at the eigendecomposition. Don't you love this word? This is so long. And we will stop here, and we will come back. I have a few more concepts to introduce and to show you how to do it in PyTorch. And then after that, during the next module, we will do the hands-on session, and we will have a lot of fun with PyTorch. If you haven't used PyTorch, you will see how. All right. So the eigendecomposition. When we have a complicated problem, we break it into smaller pieces, and then we solve it. The difference between good problem solvers and people who cannot solve problems is that problem solvers take a complicated problem, break it into smaller pieces, and solve each of them, and then put them back together. Okay? And when we deal with matrices, it is the same. We want to find independent modes in the matrix that we can that carry information that we can use. What does it mean? Assume that A is a matrix and V is a vector. All right. If I take a matrix multiplied by a vector in a way that the result is the same vector multiplied by one single number. So I take matrix A, multiply it by vector V, and as a result, I get the same vector, but it is multiplied by 4 or 2 or 0.2 or something like that, just one number. A scalar, yeah. A scalar, a lambda is just a scalar, okay? This does magic because that simple equation carries so much information in it that I'll tell you what exactly it is in a second. Let's calculate some eigenvalues. See, when you do things visually, everything is so nice and doable. And that's what I always recommend. Take something that you can see and feel and experiment with, and play with it until it becomes easy and natural. And I have shared the link to this page with you. We want to So this is our matrix. We want to compute the eigenvalues of this matrix. What do? We, oops. Let me use the board again. Where is the eraser? Oh, it's here. Thank you. So I have matrix A, and this has things in it. These are not zeros. These are stuff. Okay? And I'm multiplying it by this vector. And I'm getting a scalar times the same vector. Okay? Now, if I take this to the other side, I get this minus this equals 0, right? And then I can factor this out on the right, and I get A11, A12, A13, boom, 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 A33 minus lambda times I multiplied by V1, V2, V3, that is 0. Okay? So we have multiplied two things together. The answer is 0. What could it be? Either this is 0, so either this vector is identical to 0, which is useless. I mean, this is lame. So let's assume that it's not 0. What else can we have? You can show that you remember the determinant that we defined just before. This tells us that the determinant of this should be identically 0. We solve that, and we find our eigenvalues. All right. So here in this case, this is our matrix, 6 minus 1, 2, 3. And we want to find the eigenvalues. So we have to compute the determinant of the matrix minus lambda times I. All right? And if we do that, the determinant of this is, actually you can do that. You can calculate it yourself. The determinant is lambda squared minus 9 lambda plus 20 is 0. And we solve that equation, gives me two answers. Lambda equals 5 or 4. So there we go. We have the answer to our problem. I have two eigenvalues. Usually, if I have an n by n dimensional n squared dimensional matrix, I have n eigenvalues. All right? Eigenvalues can be all positive, all negative, some positive, some negative, some positive, 0 negative. We have all different combinations.
What are they good for?
We'll get there.
Okay.
I'll show you. If all of your eigenvalues are positive, your matrix is positive definite. It is called positive definite. All right? And if your matrix is positive definite, we will see in the third part of our series that it will lead to a convex problem, a convex function where you can actually solve your deep learning problems and get a result. Otherwise, it will not converge. You will start sliding everywhere, and it won't converge. All right? So we compute it. We see they are all positive, and that tells us that there is hope. We can solve this problem. Also, when you read the papers or when you work on deep learning, you keep running into things like this. Is this scary? It will not be in 2 minutes. To tell you what they are, let me introduce you the concept of orthogonal matrices. If Q is an orthogonal matrix, you take Q, you transpose it, you multiply the two together, you get the identity matrix. So it is orthogonal to itself. You multiply them together, you get 1. All right? The nice property that this has is, what is the matrix that if I multiply the Q by Q, I get the identity matrix? It's the inverse of Q, right? So for orthogonal matrices, the inverse is the same as transpose, which means, did I say trace before? I meant transpose. So this means, you remember I told you doing the inverse is a terrible idea. If you have an orthogonal matrix, you just take it, rotate it, you have your answer, you have the inverted matrix. So that's a very nice property. It saves you a lot of GPU time. You pay less, make more money, get rich. And now, what these are all good for, this is where it is useful. If I have a matrix that is symmetric, and if it is symmetric, that means A and A transpose are the same. It is symmetric, so if I rotate it 90 degrees, you won't be able to know, right? For every symmetric matrix, you can take the eigenvalues that I showed you, and you have n of them for n-dimensional matrices. You can form a diagonal matrix and fill it up with the eigenvalues. You can take the eigenvectors and build a matrix like this with that. So every eigenvector, you just stack them up together, and you build a matrix this way, and you transpose it. So this is a transposed matrix here. You multiply all of these together. That gives you the original matrix. All right? And that has a lot of useful properties. You can, yes?
Sorry, when you say eigenvectors, it's just like piling up, like the same eigenvalue on top of each other?
No. So eigenvector is the vector, you remember this? The vector that I multiplied the matrix by,
Got it.
and I got that vector multiplied by a number, right? So after we compute the eigenvalues, we go back, put it in there, and for every eigenvalue, you compute an eigenvector, which is a vector. So if we have an n-dimensional matrix, the n-dimensional matrix has n eigenvalues, and for every eigenvalue, which is a scalar, you have the corresponding eigenvector. And you take those n-dimensional eigenvectors, you stack them up together, you rotate them, multiply by a matrix which is a diagonal, and on the diagonal has the eigenvalues. Do all of this, it gives you your symmetric matrix. And 1 second. And this has a lot of useful, interesting properties that we will see soon when we get to optimization. Basically, what we are interested in are matrices that are easy to calculate and work with, and we don't have to do n-squared stuff, because that kills us. And as the problem gets bigger, the matrices grow as n-squared, and quickly everything becomes impossible or very expensive. Yes, we have 2 questions.
So is this singular vector decomposition?
It is very related to that. If you read in the reading assignment, we are stopping here, but the reading assignment, if you if you read the chapter of the book, the deep learning book, you will see how this is used in singular SVDs and yeah. Good eyes. Yes.
So just to make sure I'm clear, the eigenvector is a series of the same eigenscalar.
No. The eigenvector is a vector where that if I multiply my matrix with, so I have a matrix, okay? Eigenvector is a vector that I multiply the matrix with that vector, and I get the same vector out, up to a factor. Okay? So it's not made of eigenvalues.
Okay. So then where did the n eigenvectors come from?
The n eigenvectors. So I start with my original matrix, and I solve the eigenvalue problem for this.
Oh, so there's multiple eigenvectors that could work in that equation.
Yes. For an n-dimensional matrix, I have n eigenvectors.
Right.
Okay. So if you have eigenvectors and eigenvalues of a matrix, that you have all the information in your matrix. Everything is all there. Okay. And you have reduced your n squared problem to a much smaller problem. All right? Yes.
So I was just wondering, so eigenvector represents the maximum variance or the direction of the maximum variance of the matrix, right?
The maximum variance of the matrix. I haven't thought about it that way.
So for say if this is the PCA and then you find like that matrix is the data points, then the eigenvector is the...
Oh yeah, you're putting it in the PCA language. Yeah, so they it is related for PCA. You have to you do something similar, but it's slightly different. I don't want to get into that at this point, but let's read this read the section, and we can talk about it next time. All right, but these are related. Any more? Yes. So we are stopping at the hands-on part. We'll take a break. We'll come back, and we'll have a lot of fun with PyTorch.
5 minutes or 10 minutes?
10.
5 minutes.
10, 5?